Welcome to this course, EGS 211, which is electric circuit analysis intended for the electrical engineer. In this course, we'll learn to take a physical model of a circuit and represent that physical model as a schematic diagram of circuit elements. Each of these circuit elements has a mathematical model associated with it, so we'll take the mathematical model of the circuit elements and additional circuit theories and methodologies or methods to determine the behavior and characteristics of the circuit. So although this course is intended for electrical engineers, it can also be taken by mechanical engineers, is often required by mechanical engineers as well. Different fields of engineering, electrical engineering, that this is an introductory course for include control systems, communication systems, signal processing, power engineering, instrumentation design, semiconductor manufacturing, obviously computer engineering as well. So this fundamental introductory course is taken by all electrical engineers and computer engineers, as well as some mechanical engineering programs. So this course is a linear circuit analysis. So that's the fundamental subject of this course, our EGS 211. So what do we mean by linear? What about nonlinear circuit analysis, considering that most circuits are nonlinear in nature? Our diode is nonlinear in nature. Our transistor is nonlinear in nature. So why do we study linear circuits? The reason is primarily that they're easier to study. Linear problems are inherently easier to solve. So we can use linear approximations or models for these physical situations. It's also true that most systems behave linearly over a range of operation. That range of operation includes the range of temperature, a range of frequency, range of current or voltage. So if we look, for example, at the bipolar junction transistor, often referred to as the BJT, which is fundamental for all computer designs, also MOSFETs, but we look at the current versus voltage relationship in this BJT, we see a very nonlinear, if we take any one of these curves, each of these curves are related to a different base current, they're very nonlinear over the range of voltage from 0 to what we have this BVC, breakdown voltage is what this is referring to. So it's very nonlinear if we take the entire range, but if we look at this range here in white, this is an active region. This is where we want to operate the transistor in linear mode. So in here it's behaving linearly. So as long as we make the correct assumptions, we know the voltages over which we are analyzing the transistor, we can also use a linear model for that. If we look at a mathematical example of our exponential function, e raised to the power of x, well, that's clearly not a linear function. However, if we take this, and I've put this into Excel, and we have our value of x ranging from 1/10,000th to 3, and we look at the result of the e to the x, we look at the result of the linear model, x plus 1, and then we look at the percent error. If our e to the x function, diagrammed here, is going to look very nonlinear. Our x plus 1 is a linear function. If we look at the percent error, if x is less than 1/100th, we have to 3 significant digits 0% error. If it's less than 1/10th, we're still less than 1% error, only 0.5% error. If we jump to 1, we jump to 26% error. So we're somewhere between 0.1 and 1.0, we exceed a 1% error. So depending on your error tolerance and your range of x, you could model e to the x as a linear model of 1 plus x. So that's an example of being careful of your assumptions. So our conditions of linearity exist for our theories to apply. That's the assumption we're making in this course. So our linear circuit analysis has 4 different, I guess we'll call them subcategories here. We'll start out looking at DC analysis. DC stands for direct current. So all the charge just moves in one direction in a DC circuit. It's typically powered by a battery. So we say that the parameters, electrical parameters, are not changing with time, so we don't have to be concerned about time when we're doing our DC analysis. We'll then look at transient analysis. And then our circuits are suddenly energized. We're going to turn on or off a battery. So turn on or off a flashlight. And that's going to be important when we add inductors and capacitors to our resistive circuits. So this is going to really be our study this semester. Next semester, we'll start looking at AC analysis, alternating current, where the current flows in both directions. We have sinusoidal type currents. We'll start out looking at sinusoidal type currents, and then we'll look at a variety of different current sources. So those energy sources can continually change with time. And then when we have that type of situation, then we can do a frequency response analysis. So we'll look at power, frequency response, and then we'll look at other types of energy other than sinusoidal. And that's what we'll do next semester. So we'll start out also looking at resistive circuits. A flashlight is a resistive circuit. A toaster is a resistive circuit. The quantities in resistive circuits do not change with time. When we talk about quantities, we're going to be talking about voltage and current and power. We'll introduce those shortly. So the circuit analysis techniques that we'll use, we'll start out looking at just Kirchhoff's laws and Ohm's laws. Those are the basis to all circuit analysis, and then we'll put on top of them techniques and methodologies of nodal and mesh analysis, superposition, source transformation, and Thevenin and Norton theorems. We'll become very good at that, and then we'll start looking at transient analysis, where we add to our inductors and capacitors to the circuit, and we see what happens as things change with time. Now our equations will involve time. Our circuit equations will involve derivatives and integrals. So we'll be able to use the same powerful circuit analysis techniques, but we'll now be using integral differential equations. So it'll become a little bit more difficult. And when I say difficult, I mean more difficult mathematics in the model, but creating the model or creating the analysis is really just the same. So from there, however, when we get to integral differential equations, when they get to third order or fourth order, it obviously becomes pretty cumbersome. So we'll start introducing next semester our AC analysis, and we'll be able to take our sinusoidal currents and voltages, we'll model them as RMS values of current, and we'll use a phasor analysis where we'll convert our integral differential equations in time domain to algebraic equations in frequency domain. From there, we can look at frequency response, we can look at filters, and we'll be using Laplace and Fourier analysis to convert between time and frequency. So we'll be doing this at about the same time that you're learning that in differential equations. Or perhaps you've already had differential equations. So our relationship of circuit analysis to engineering, we really need to understand what we have is a methodical approach to problem solving. It's great to be creative, but we also want to have methods that we can check for our accuracy. Our mathematical equations that describe the circuit behavior closely resemble equations of other studies of engineering. I mentioned that mechanical engineers are often required to take this course because the mathematical models of circuits have analogs in electrical engineering. Those analogs, for example, of voltage, the analog to that can be a force. Charge, the analog to that can be distance. Resistance in a circuit, the analog to that is friction or friction coefficient. So when we're modeling problems, we're going to start with a physical model. We're modeling something in the real world. In order to model that, we have to come up with mathematical models, so we'll have circuit elements that we can use to represent how that physical model will behave. So we'll model that mathematically with circuit elements, but we also then want to have our language model. We want to be able to talk about the circuit instead of just in terms of mathematics. We want to be able to have our language associated with that. So those are our goals for this class, that we become very good at modeling circuits, and that we understand how to use problem solving. We get better at problem solving. A huge goal in this class is to improve our problem solving abilities. Basic problem solving, we need to have a fundamental understanding of the scientific principles. The scientific principles here are the principles of electricity and magnetism. We just need Newton's classical physics for electricity and magnetism to be able to understand or be able to work with linear circuit analysis. We take that and we have our practical knowledge in mathematical terms in this case. So that's the mathematical models of our circuit elements. With a little creativity and so that we can apply the correct methodologies, the correct theories, then we get a solution to that problem. So there is creativity involved in both analysis, but there's even more creativity involved in design. If we know what we want to create, we know the science behind it, we know the theories, the circuit theories, then we can use some creativity to design models. So the difference between analysis and design, although this is an analysis course, we will do some simple design work as well. But analysis, the great part about it is it has a unique solution. We need to determine the scope of the problem, obtain information required to understand it, and compute the parameters that we're interested in. And there should be a right or wrong answer. When there's design, there's no unique solution. So we're synthesizing something new that's part of a solution to the problem. But after we do that, we need to be able to analyze it to see if it deems being correct. Or perhaps we don't know correct, that it deems being at least feasible. So one way to do that analysis is with computer analysis. When we're looking at very big electrical designs, we will want to use computer analysis. We'll create a schematic drawing using programs such as SPICE or PSpice for the PC, or general ASIC and circuit board, application-specific integrated circuit board layouts with a component library. They may be manufacturing specific or more general. So these are very valuable tools to be able to use, but they're no replacement for that paper and pencil analysis. So we're going to be working for the first few weeks just doing our paper and pencil analysis before we introduce computer analysis. Although computer analysis is a good way to help you verify that your analysis is correct. So when we talk about analysis, what we're talking about is problem solving. And problem solving is really what can be very frustrating for most students. So problem solving strategies and techniques is something we want to get good at in this class. So, how to start a problem is typically the most difficult thing to do. When we look at a problem, what we're going to want to do is mathematically model it. So what we want to end up with is a complete set of equations, and we want to be able to organize those equations in a manageable way. So a consistent and methodological approach is what we'd like to use. The textbook goes over a flow chart that we'll look at the next page, and at North Shore Community College we work on this 5-step process. So we will associate both of those, and we'll keep stressing that 5-step process and get you really good at problem solving and comfortable at looking at a problem that you are not familiar with and being able to associate that problem with perhaps problems that you are familiar with or you have seen before. But the key is practice. You have to practice, practice, practice until it becomes like a flow. The problem solving becomes a flow, and you actually enjoy doing it like you're in the zone if you play sports. So you want to be able to do it in a relaxed environment, an environment that you can feel comfortable in. So if we look at this flow chart, we have a problem. We want to read the problem statement carefully, however that problem is stated. Slowly, carefully, perhaps jotting it down again in our own words, so we can identify what is the goal of the problem, what is the outcome that we want. So in doing so, what we have to do is collect all the known information. These are, if we look at our 5-step process, the known information is what's been given, what is already understood. Those are our givens. The goal might be what it is that we're trying to find. So once we know that, then we have to look at what do we know? What are the scientific principles we know? What are the circuit theories that we know? What methodologies do we know? Or techniques that can best fit the problem. So how can we then construct an appropriate set of equations? What we have to do within here as well is draw a diagram. Diagram is quite important, and it's not really listed in this flowchart. But the goal is to come up with an appropriate set of equations. If you have 4 unknowns, 4 things that you're looking for, then you need 4 equations. If you don't have 4 equations, you got to go back and understand the problem again, collect more information, or perhaps more theories so you can come up with another equation or reduce the number of unknowns. If you have the same number of equations as you have unknowns, then you can attempt a solution. At that point, you have to verify the solution. You're not really done yet. If it's a homework problem, you can look and see if you got the answer correct and say, okay, good, I'm done, I got it correct. What we want to do is also do that check. What that check is it reasonable? Is it what's expected? If it's not, if you got the wrong answer, then you got to go back again. Or if it just doesn't make sense, if you don't have the correct answer. So if we're looking at our 5-step problem solving, once we get this solution, we've worked through our mathematical process, does that solution make sense in terms of what you know? How can you associate that solution to other problems that you are already familiar with? How can you associate the solution to real-world problems? And this last step, where you're analyzing the results, this is where you're going to get really good at circuit analysis, really good at problem solving. It's also the step that you'll probably take the least time with initially, because you're going to be working so hard on determining what the problem statement means, so you can understand the givens and assign it to the variables and what you're being asked for, and you're working with your theories and strategies and assumptions. So I'm going to stress now, and we'll continue to stress throughout the class, this 5th step: analyze the results. Does it make sense? What other problems have you seen similar to this, and being able to compare them. That's where you'll become, that's your real critical thinking, and a very important part of this class. So with that, we'll leave you with this video, and I'll see you in class